as we move into these two sections from Chapter 8 that we're going to go over, we switch gears again and we move on to empirical and theoretical probability. We need to get some definitions out of the way first. An experiment is a controlled operation that yields a set of results. So first, let's define experiment as a controlled operation that yields a set of results. I want to point out that experiment and empirical both start with E, so when we're talking about empirical probability, we're talking about experiments. The outcomes are those possible results of the experiment. And I say possible results because not every result is possible, right? If I'm rolling a fair die, I cannot roll a 7 because there's only 6 sides on the die. Event is a sub-collection of the outcomes. For example, let's go ahead and talk about rolling a die. If I'm rolling a standard die, my set of outcomes, or let's do this. Let's say roll a single die. My set of outcomes would be my sample space. I can roll a 1, 2, 3, 4, 5, 6. If I'm interested maybe in the event of rolling an even number, if E is my set of even numbers, then that would be the outcomes just 2, 4, and 6. Okay, empirical probability. Like I said, empirical and experiment start with E. That's going to be your tie together. Empirical probability is the relative frequency of an event based on actual observations. The relative frequency of an event based on observations. Empirical is like experimental probability. When I talk about the probability of an event, I'm looking at the number of times the event occurs compared to or divided by the number of times the experiment is performed. So I'm not comparing, for example, if my event is rolling an even number, theoretically, I've got an even chance, at rolling an even number because 3 of the 6 outcomes are all even numbers. So I've got a 0.5 probability, or 1 out of 2, or 3 out of 6. But experimentally, I could roll a die 10 times and never roll an even number, and then my empirical probability would be 0 out of 10. Or maybe I rolled the die 10 times and 9 times out of 10 it rolls even. Well, then my empirical probability would be 9 out of 10 instead of what we expect theoretically. And that leaves us into our other type of probability statement. Theoretical probability is when frequency is determined by a study of all possible outcomes. The frequency of an event is determined by a study of, by looking at, by analyzing all possible outcomes. And another name for all the possible outcomes is my sample space, which is designated S. Right there, my sample space, the list of all possible outcomes if I roll a standard die, would be 1, 2, 3, 4, 5, 6. If I'm dealing with theoretical probability, my ratio looks like the number of outcomes in E compared to the number of possible outcomes. So theoretically, if my event is rolling an even number, theoretically, the probability of rolling an even number would be 3 out of 6 or 1 out of 2 if I simplify it. Theoretical and experimental or empirical probability are not always the same because one is based on all the ways things can happen and the other one is based on an experiment or a set of trials. All right, law of large numbers. When we're performing experiments, like I said, I could roll a die 10 times and never get an even, or maybe I get all evens. But the more times I roll, the closer my outcome gets to being the same as the theoretical probability. So the probability applies in practice to large numbers of trials. Not a single trial or small set of trials. So what the law of large numbers tells us is that the relative frequency in the long run is predictable. The more trials we do, the more we expect our outcome to approach our theoretical probability. Okay, 4 important probability facts. The first one is that if I want to say that the probability of something is impossible, then that probability is 0. If something is a sure thing, certain outcome, the probability is 1. Which means every possible probability has to fall between those two values. What does that mean? Well, I'm never going to have a negative number as a probability, and I will never have a number greater than 1 as a probability. And finally, if I add up all the ways things can happen, it's going to equal 1. So for example, if I take the probability of an event E and add it to the probability of everything that's not that event E, I get 1. And further from that, I expect that to figure out everything that is not my event E, I can do 1 minus what is. Okay, let's do an example of that. Let's go back to our dice rolling probability. If my event is rolling a 3, well, the probability of that event, the probability of rolling a 3 is 1 out of 6 because there are 6 different outcomes of rolling a die and only one of those outcomes is a 3. So that's the probability of my event. What's the probability of not rolling a 3? Well, it's everything else, which would be 5 out of 6 outcomes. So that if I add the probability of my event to the probability of the complement of everything else, I get 1. And if I'm trying to figure out the probability of that complement, of it, in this case it not being a 3, I would do 1 minus the probability of rolling a 3, which gives me that 5/6. Okay, I think that my notes got a little sideways. This heading should be on the next page, but that's okay. We will work it out. Empirical probability. Just a reminder, and yes, this absolutely was supposed to be on the next page. Empirical probability is my experimental probability. Experimental probability. And the probability of my event is the number of outcomes that I'm interested in out of the number of trials, the number of times the experiment is performed. Okay, I'm disappointed that my pages got a little messed up, but we're going to roll with it, and it's going to be okay. Alright, so here we go. Several friends went fishing, and they caught 4 different kinds of fish, and this is how many they caught of each type of fish. So we're asked to find some empirical or experimental probabilities. Now these are experimental probabilities because it's based on an experiment, based on them actually catching fish and on the reported numbers that they caught, which means that we need to know the total number of fish that were caught so we can put that in our denominator. So let's look at that. Let's add those all up and see what we get. We have 55 fish total. So if I want to know, if I go to that same lake, what is my expected probability? What's the chance that if I catch a fish it's going to be a grouper? Well, they caught 13 groupers out of 55. What's the chance that it will be a flounder? Well, they only caught 3 flounders out of 55. What's the probability that I will catch a shark if I catch a fish? Well, that's going to be 20 out of 55. And then finally, a kingfish would be 19 out of 55. Now, these fractions don't mean a lot to us because out of 55, we have a hard time picturing that. We can compare and we know, okay, so the shark was the one that was caught the most with kingfish really close. Definitely there weren't many flounders, so the chance of catching a flounder isn't very good. If I look at this equation here, the probability of a grouper plus a flounder plus a shark plus the probability of catching a kingfish. Well, when you add fractions, you only add the numerators, and if I add these all up, I just did that there, that would be 55 out of 55, or 1. So that represents the whole thing. The sum of the probabilities of all possible outcomes is 1. Now, what if we wanted to make this a little more applicable to us? We could change this. We could always simplify fractions. That I could simplify, but then my denominator is just different, and it doesn't really help me. Sometimes it will ask you to do a probability as a decimal. Let's go ahead and convert these to decimals, rounded to the 2 decimal places. So if I do 13 divided by 55, I get 0.24 if we round that. So that would be about 0.24. That would be my probability of catching a grouper. 3 out of 55, that would be about 0.05. Not a very good chance. 20 out of 55 gets me to 0.36. So about a third of the fish in the lake we think are going to be groupers, or at least the ones who are sharks, not groupers, good grief. Sharks, at least the ones who are wanting to be caught. And then kingfish, 19 out of 55. It's going to be really close to that one. Yeah, it's going to round to about 0.35. Now, if I add up these decimals, these might or might not all add to 1. In this case, because of the way we rounded, we're in good shape. It's going to add up to 1. But whenever I do an approximation, sometimes when I try to look for that total, it doesn't come out exactly right, and that's because of rounding. Let's answer the rest of these questions. So the sum of the probabilities of all possible outcomes is 1. What's the probability of an event that is certain to occur? The event that if I catch a fish, it will be one of those 4 would be, the probability would be 1. That's a sure thing. What's the probability of an event that cannot occur? So let's say that I go fishing in that lake and I catch a largemouth bass. Well, there aren't any largemouth bass, so that probability would be 0. So the probability of an event must be between 0 and 1. And if I add the probability of an event to its complement, everything in this case that is not A, the sum of those things is 1. Okay, so that was our focus on experimental or empirical probability. Remember, by definition, theoretical probability is when we are basing it on the sample space. So the probability of an event is equal to the number of total outcomes that fit that event out of the number of possibilities in the sample space. All the ways things could be. For example, each individual letter of the word Tennessee is placed on a piece of paper, and because there are 9 letters in Tennessee, 9 pieces of paper are placed in a hat. If one letter is selected at random from the hat, determine each probability. What is the probability that I'm going to pick an S? Well, I've got 9 letters in the hat, and 2 of those are S. What's the probability that it will not be S? Well, if 2 of the 9 are S, that means the other 7 are not S. That's a complement. Together it adds up to 1. 9 over 9 or 1. What's the probability that it would be a consonant? Well, we've got consonants and vowels. In this word, E is the only vowel. There are 1, 2, 3, 4 E's, so that means there must be 5 consonants. What's the probability that it would be a T or an E? Well, we already said there's 4 E's, there's 1 T, so that would be 5 out of 9 slips of paper would have a T or an E. What's the probability that I would draw a slip of paper that would have a W on it out of these 9 slips? Well, there are no W's, so that is not possible. The probability is 0. What's the probability that if I draw a letter of Tennessee, it's going to have a letter on it that is not V? Well, these are all not V, so that's a sure thing. Make sure that you read these questions carefully. Okay. Another thing that we do with probability other than rolling dice is decks of cards. So we're going to talk about a standard deck of cards. And once again, my pages are off just a little bit. I hope that I get these fixed before we, you know what, I'm going to make myself a note to fix the pages so that I can remember to do that before I print these for you, and your notes will look better than mine. So fix the pages. Okay. So deck of cards, and my deck of cards is at school, and I am at home making these videos, so I don't have a deck of cards. But a standard deck of cards has 4 suits, and I will sketch those on the next page, but there are a total of 52 cards in a standard deck. And standard deck of cards, I just mean cards that you play card games with. So if you play poker, or you play spoons, or you play hearts, or any games like the Go Fish, well, there are special Go Fish decks, aren't there? Anyway, 52 cards in a standard deck. 52 total cards. And in those standard decks, there are 4 different suits or pictures. So I'm dividing the 52 cards up into 4 equal suits. That means there's going to be 13 cards in a suit. Well, what do those suits look like? There are 2 black spades, and I am not an artist. Spades are black, and clubs are black. It's like a little 3-leaf clover. Spades and clubs are black, and hearts, that one's easier, and diamonds are red. So I've got half the deck is black, half the deck is red. 13 cards in each suit. So 13 spades, 13 clubs, 13 hearts, 13 diamonds for a total of 52 cards. And the different cards in the deck, we start with ace high usually. Ace can be low though. Number cards 2 through 10. Then you have jack, queen, and king. So there's 1 of each of these in spades, 1 of each in clubs, 1 of each in hearts, 1 of each in diamonds. So that means we would have 4 kings, 1 of each. Okay, if you have a deck of cards and you're not familiar with it, grab it. We will have decks of cards to do an activity if you're coming to class to talk about this. Alright, 1 card is selected from a deck of cards. Determine the probability. Now we're working on theoretical probability, so that means our denominator is going to be 52 because my sample space has 52 cards in it. Out of those 52 cards, how many are 5s? Well, I have a 5 of spades, a 5 of clubs, a 5 of hearts, and a 5 of diamonds. So 4 out of 52 are 5s. If I want to simplify that, I check, and 52 is divisible by 4. So 1/13 of the deck is a 5. The probability of selecting a 5 at random out of the deck is 1 out of 13. What about not a 5? Well, it's either 5 or something else. This is the complement. If there are 4 5s, that means there must be 48 cards that are not 5, which is going to simplify to be 12 out of 13. What about specifically the 5 of diamonds? Well, there's just one of those. So the probability of drawing the 5 of diamonds randomly out of the deck of cards is going to be 1/52. What's the probability of drawing a card at random and it being black? Well, half the cards are black, so that's my probability. 26 out of 52 cards are black, which is 1/2. What's the probability that if I draw a card out of a standard deck at random, it will be a diamond? Well, diamonds are 1/4 of the deck. There are 13 diamonds out of 52 cards. Now things start getting interesting. A king or a club. Well, I've got 13 clubs. One of those is a king. I have a king of spades, a king of hearts, and a king of diamonds. So 13 clubs, 14, 15, 16 to add in the rest of the kings. That will simplify. Those are both divisible by 4 to 4/13. A king and a club. A single card that is both king and club. Well, that's going to be just that one card, the king of clubs. What about the probability of drawing an ace? How many aces are there? There's an ace in each suit, so that's 4 out of 52 cards that are aces, and that simplifies. Both of those are divisible by 4. What about a card that is specifically the ace of spades? Well, there's only one of those out of all the 52 cards. If you haven't already tried some of these on your own, I encourage you to pause the video and see what you can do with these next 6 without following along, and see what you get if you get the same thing as me, and come back. Or means it can be one or the other. I have 4 different 5s. I have 4 different 10s. So the chance of drawing a 5 or a 10 would be 8 out of 52 cards, which is going to simplify to 2 out of 13. A card that is a 5 and a 10. So we're drawing one card. What's the chance of drawing a card that is both a 5 and a 10 card? Well, there is no 5-10 card. That's impossible. What's the probability of drawing a red card? Well, it's the same as drawing a black card. Half of the cards are going to be red, so 26 out of 52 cards are going to be red. Hearts, that's one of my 4 suits. There are 13 hearts out of 52. 1/4 of the deck is going to be heart. What's the probability if I draw a single card that that card will be either red or black? Well, that's every card. Every card is either red or black, so that's a sure thing. What about drawing a single card? What's the probability of that card being both red and black? Well, there are no red-black cards, so that is impossible. That probability is 0. Okay, I've got another heading that belongs on the next page. That's okay. We're going to draw a line right there and work with what we got. Something else that we work with a lot, tossing coins. So we take a fair coin, so think a quarter, and we toss it 2 times in succession. So we're doing 2 tosses. Sample space and probabilities. Now we're doing, we are setting up what could be termed an experiment, but we want the sample space. So theoretically, what are all the ways this could happen? Well, we're going to set up a tree diagram. We're going to set up a tree diagram to show how all the ways things could happen for 2 coin tosses. So we've got 1 coin toss, 2 coin tosses. And now if we're tossing a quarter, it's heads one side, tails the other, right? So that first toss could either be heads or tails. And then the second toss, does it depend on the outcome of the first toss? Well, no, because I picked that coin up again. Oh, look at that. I've got a quarter right here. So I've got my quarter. I tossed it. Whoops, and it tossed off the page. I tossed it and it landed on tails. So when I pick it up again to go for the second toss, it doesn't matter what it landed on the first time. It still has heads or tails. So my second toss is either heads or tails. So how many different outcomes are there for those two coin tosses together? Well, either I can get heads on the first, heads on the second, or I could get the next branch, heads on the first, tails on the second. Next branch down, tails the first time and heads on the second, or tails the first time, tails on the second. This is an organized list. Two different ways to show the sample space. We've got a tree diagram with branches, 4 branches, or an organized list showing 4 outcomes. So let's go ahead over here. Sample space could be heads, heads, heads then tails, tails then heads, or tails both tosses, tails and tails. Alright, let's answer some probabilities. What's the probability when I toss a coin twice in a row that I will get heads both times? Well, that only can happen 1 out of 4 different ways, so I expect a fourth of the time I would get both heads. This is theoretical probability. It's based on my sample space, all possible outcomes, not based on an experiment. I'm not actually tossing the coins. What's the probability that I get tails both times? Well, 1 out of 4. And that's just what that is. There is no equal to. What's the probability that I get the same outcome? So that would be either both heads or both tails. Well, that's 2 different ways out of 4, or half. My probability is 1 out of 2, or 0.5. What's the probability that the outcomes are different? Well, that would be a heads then tails, or tails then heads. So again, 2 out of 4, or half, 0.5 probability. What's the probability that I would get a head on the second toss? Well, head on the second toss, that happens twice here. So that would be 2 out of 4 outcomes, or 1/2. And then finally, the probability that I get at least 1 head, well, that would be 1 or 2 heads. So that's 1, 2, 3 out of the 4 possible outcomes, or 3/4 is that probability. All right, excellent. Now, geometric probability is supposed to be the heading for this last page of notes for this section. So let's come over here and let's set that up. This is our geometric probability page. The spinner shown has 4 sectors labeled R for red, Y for yellow, B for blue, and G for green. An experiment consists of spinning a pointer once and recording which color the pointer lands on. And this is my example pointer. So like I've spun it, it landed on yellow. What's the sample space for this experiment? What are my possible outcomes for this experiment? Well, it can be red, yellow, blue, or green. So my sample space are those 4 colors: red, yellow, blue, or green. Since the blue sector is 1 out of 4 equally sized sectors, the probability that if I spin my spinner, the pointer will land on blue would be 1 out of 4, because they're all the same size. So find the probability of each of these. Well, the probability it would land on green is also going to be 1 out of 4. Yellow or green. Well, yellow and green together take up half of the space. What's the probability that whatever color it lands on will not be red? Well, this is red, so that's going to be 3/4 of the spinner. Geometric size probabilities. Okay, now notice that these spinners are different. This spinner is the same as this spinner. I've just illustrated how much of the space that blue takes up. Are the events here, blue and green, equally likely on this spinner? Well, no. Blue is twice as big, takes up twice as much space as green. So it's going to be more likely because it takes up more space. Imagine, okay, so that's, just so you can get your proportions correct, if we think about fourths, this would be 2/4 or 1/2, 1/4, 1/4. So the probability of spinning and it landing on blue is going to be 1/2. It takes up half the spinner. Blue or green, well, that's a total of 3/4 of the area of the spinner. So make sure you're paying attention. Okay, so this one is interesting. stop and think about how you could divide these into equal sectors. Well, it looks like I could divide right there, and I would have 6 equal sectors where blue is 1, 2, 3 of them. So blue would be 3/6 or 1/2 of my spinner. The probability in landing in yellow would just be 1/6. What about yellow or blue? Well, blue is 3, yellow is 1, so that would be 4/6 or 2/3. What about the probability of landing on something that is not green? Well, green takes up 2/6, so that's going to be the other 4/6 or 2/3. Alright, so that's just a little bit different look at probability, the geometric probabilities.